Welcome back, students. We are now going to look at the case of many electron atoms. As chemists, of course, we're interested in atoms other than hydrogen. And so now we're going to discuss the Schrödinger equation solution for atoms other than hydrogen. And what we'll get to today, the conclusion of our lecture today, will be the quantum mechanical version of Pauli's exclusion principle that we know from Gen Chem, namely that electrons have to have different spins, or that every electron has to have a unique set of quantum numbers. Maybe you've heard it in either of those ways. And we're going to see what it is quantum mechanically, and then how that kind of boils down into this easier version that you learned in Gen Chem. So the learning goals for today are going to be to explain why we can't solve the Schrödinger equation for multi-electron atoms. Then we're going to come up with a couple of assumptions that are used to approximate the multi-electron atom energy. And then next time we'll see how computers go about trying to be more accurate than we can with pen and paper. We'll see the quantum mechanical Pauli exclusion principle and apply it. And we'll get to this thing that we learned from Gen Chem, that electrons have to have a unique set of quantum numbers to have more than one electron in an atom. We'll end up using matrix determinants here, and I'll go over 2x2 determinants in this lecture, and we'll go over a trick to do 3x3 determinants in class. And you're going to want to be able to be comfortable doing these simple determinants, and much more complicated determinants we'll generally not do in class, because they're basically just bookkeeping, and that's really not fun or interesting. So let's move into the Schrödinger equation for these other atoms. And last time and the time before, we described the Schrödinger equation for the hydrogen atom, and that was great. And we got these solutions, and these solutions are these orbitals, and we know them, and that's awesome. And now we want to move on and describe the helium atom, which is the second most simple atom that we can have. So I want you at this point to pause the video for a minute and think a little bit about the energetic terms that we would need to account for to accurately describe the total energy of the helium atom. Before you do that, remember that for hydrogen, we needed to know the kinetic energy of the electron, and then we also needed to know the Coulombic attractive force between the electron and the nucleus. So with those in mind, pause the video here and think a little bit about what we would need to know to describe the helium atom. All right, I hope that you paused the video and came up with the ideas that we need to solve for the helium atom. Now, the difference, of course, between the helium and the hydrogen atom is mostly the fact that the helium atom has a second electron. The nucleus, of course, is different, but it's still just one nucleus that has a positive charge of 2 now. So how should we describe the helium atom? Well, we need to know the electron's wave function, right? And they're both in the 1s orbital, but how can we describe the wave function for this atom? So the terms that we would need to put into the Schrödinger equation are as follows. We need the kinetic energy of electron 1, and that's shown in this term here. The kinetic energy of electron 2, that's shown in this term here. Then we need the attractive force between electron 1 and the nucleus, the attractive force between electron 2 and the nucleus, and also the repulsive force between electron 1 and 2. And that's shown here. So we have a minus 2e squared now because our nucleus has a charge of 2. So we have plus 2e times minus 1e for minus 2e squared. And then we can have 2 distances between our electrons and the nucleus, and then the distance they have amongst themselves. Here in this equation, we have made a couple of variable pools to make these things easier. Hopefully you can see that my R1 and R2 here are bold. That indicates that they are vectors. So this R1 vector is R1 theta 1 phi 1. It describes the coordinates of electron 1, and the same goes for R2. So this function is actually a 6-dimension function. There are 6 different variables built into this. We also have this nabla term here, and this nabla term is simply a condensation of the kinetic energy part of the Schrödinger equation. So when we write this nabla squared for electron 1, what we mean is the following. This whole equation, the whole kinetic energy part of the Schrödinger equation for electron 1. in spherical coordinates. So again, a very gross problem, especially even compared to our hydrogen atom. Now, unlike all the previous Schrödinger equations that we set up in class, this equation is not solvable. And this is likely not immediately obvious to you if you're not mathematicians, and we're mostly chemists, so this isn't obvious to us. But it gets into something called the three-body problem. We cannot analytically solve a differential equation that involves three separate masses, in this case, a nucleus and two electrons. This is true for our helium atom here. Another common example would be describing the gravity of the Earth, the moon, and a spaceship trying to get to the moon. Now, we can obviously send people to the moon, so there must be some way that we can get around this three-body problem. And the best way to do this is going to be to use computers to solve it numerically. They're going to take an iterative approach to find the best solution, and we'll look into that a little bit next time. However, what we're going to do today is look at some simplifications that we might be able to use to approximate and get a general idea for what the solutions to this equation are going to be. All right, so I mentioned all of these terms here. Now, what are these simplifications that we're going to use? There are two, and the first one that we'll talk about is going to be called the orbital approximation, and then the effective nuclear charge approximation. And you're likely somewhat familiar with these kind of ideas, even if you haven't heard them in this term. So the first approximation, the orbital approximation, is based on the idea that electrons in different orbitals have different chemical properties. And we are very comfortable with this assumption in chemistry. This goes all the way back to things like Gen Chem, where you say, well, we're not going to care about the core electrons, and we're only going to treat the valence electrons. And oxygen, therefore, reacts something like sulfur because they both have 6 valence electrons. And so this approximation is a pretty good approximation that these electrons are very different. And so what we're going to do in this case is, instead of treating our wave function as the function of, say, n electrons, we can rather treat our wave function as the product of n wave functions that each depend only on one electron. And so in this case, we would have our phi1, which would be, say, the 1s orbital, and then we have our variables here, our 1 theta 1 phi1, and we could say maybe we have 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, 4 electrons in the 2p orbital, and that's our wave function. And this is a pretty good approximation because we know this is something that's pretty true, that electrons in different orbitals do behave differently. So we can roughly split this wave function apart. Now, the second approximation, the effective nuclear charge approximation, is significantly less good. Now, the reason that we can't solve the three-body problem that I mentioned in the last slide is because we can't account for how two bodies, say 2 electrons, affect the motion of the nucleus, or how the nucleus and 1 electron affect the motion of the third electron. That breaks our spherical symmetry, and we can't actually solve that problem. So to get around this unsolvable problem, what we're going to do is ignore the interaction that the electrons have. And so what we do is we're not actually ignoring the electron repulsion. So electrons are going to repel each other because they're these negatively charged things. But what we're going to do is ignore the electron correlation. So for example, if I had a positive magnet and 2 negative magnets, as I move the negative magnet around, the other one would move accordingly because they're going to repel each other. And that's the motion that we can't quite describe. So how could we somehow handle this and deal with some electron interaction but ignore this correlated movement? And essentially what we do is we're going to think of our second electron as being spread out over its entire orbital. So we can think about the helium atom being 1 nucleus that's positively charged and 1 electron that has spread its electron density around the 1s orbital, and then the third electron moves in that. And so what that gets us is this effective nuclear charge approximation. And I'm pretty sure you've heard these words before when talking about, the size of atoms and so forth. So what this does to our Schrödinger equation is the following. Our 1s orbital, instead of looking like it was before, would now look like this, where instead of having a 1r in the numerator of the exponential and a 1 over a naught in this normalization term, we have zeta, where zeta is our effective nuclear charge. And so this would talk about, if we have a negative electron spread out over the helium atom, at some points, if you're closer to the nucleus where the electron is more likely to be, maybe your effective nuclear charge is one thing. If you move to a different spot, maybe you now have more electron in the way, and so your effective nuclear charge is less as you move further away. And this kind of gets around this thing that we can't deal with, namely how these electrons are correlated. Now, I also want to point out here that this equation is also how we would solve for one electron atoms that aren't hydrogen. So if we wanted to say, what is the Schrödinger equation for a helium plus ion, right, that has one nucleus, one electron, we can describe that. And our effective nuclear charge in that case would be 2. So we would put a 2 here and a 2 here in the 1s orbital, or any other orbital that we want. And this would give us the new Schrödinger equation. And we could do this for like a lithium 2+ ion as well. We would put a 3 there and so forth. So we can describe electrons with heavier nuclei, but it's still one electron, or atoms with heavier nuclei, but still one electron in this way. The last thing we want to discuss is actually two things: are electron spin, and then we'll talk about electron indistinguishability after that. And so if you go back to Gen Chem and the quantum numbers you had to remember, you'll remember that there were 4 quantum numbers, and we've only discussed 3 of them. So we are still missing this ms quantum number that was plus or minus 1/2, that was the spin number for the electron. And we're going to go and introduce that here. So thinking back to the Stern-Gerlach experiment that we used to show that we had non-commutation of, say, the 2 angular momentum operators, what we saw is that if we were to put silver atoms with one s unpaired electron into a magnetic field, we get splitting into 2 and only 2 beams. And we're somewhat comfortable seeing this spin up and spin down. Now, what this is showing, right, is that silver is having some sort of angular momentum. However, its unpaired electron is in the s orbital, which has an L equals 0. So it's the angular momentum is not coming from the s orbital. It actually has to be coming from the unpaired electron itself. And we call this electron spin. When this was initially proposed, it was thought that electrons were actually spinning like planets, revolving as they, as they orbit the sun, they rotate like Earth. Of course, the electrons aren't orbiting the nucleus and they don't really spin, but the name that we have still has stuck, and so we call this electron spin. Just like orbital angular momentum, right, we have our electron angular momentum. And so all of the same rules apply here. So what we have is we have some angular momentum s instead of L. And we should have 2 s plus 1 possibilities for the m sub s, right? So just like if L was equal to 2, our m sub L was -2, -1, 0, 1, 2. So we had 5 options for 2L plus 1. We have 2s plus 1 is the same sort of thing. Now we can use the physically observed options to figure out what our s quantum number is. So how many options do we get? Well, we only see 2. We have spin up or spin down. So that means we need to have a world where we have 2s plus 1 is equal to 2. And that gets us an s of 1/2. And therefore, m sub s, that goes from -s to s in steps of 1, gives us the options of plus 1/2, minus 1/2. And so you can see this quantization as well is too small for orbital angular momentum, which is another indication that something else is going on. So we have these new spin quantum numbers that are +1/2 or -1/2. Now, what we want to do is try to incorporate these spin quantum numbers into our Schrödinger equation. And how can we do that? What we're going to do is simply introduce other functions. And these other functions are going to account for the spin. So these are called spin functions, and we're going to incorporate them with spin formalism into our Schrödinger equation. So we're going to give these two functions, alpha and beta, where alpha is spin up and beta is spin down. And these are going to be eigenfunctions of the s² operator and the sz operator, which are exactly the same as the L² operator and the Lz operator. So what's going to happen is we can operate on our eigenfunctions here, so alpha or beta with s², and operating on these with s² returns the magnitude of the angular momentum vector. And just like L² gave us h⁻² L plus 1 when we operated that on an eigenfunction, our s² operator does the same thing. So if we operate on our spin up with s², we get h⁻² s plus 1 times our function. And that, of course, is here. Our s is 1/2. And then when we get, when we do it on beta as well, we get the same thing. It's the same magnitude of that vector. And we'll also have s sub z operators. And if we operate on our functions with s sub z, we return our quantum number ms, just like ml times h bar. And in this case, ms is ±1/2. So if we operate on alpha with sz, we get +1/2 h bar over 2. And if we operate on beta with s sub z, we get negative h bar over 2 times our beta function. So these functions that we have are still, they're eigenfunctions of these operators, and they're also eigenfunctions of the total energy operator. So if we want to put these things together to get a complete wave function, we can simply do that. Now, how we make these things part of an orthonormal set like they would need to be if they're eigenfunctions is simply by defining that they are. So if we take the complex conjugate squared of alpha and then integrate that over its respective variable, which we call sigma, and when we do the same thing with beta, those are 1 because we're normalizing these functions. And since they're orthogonal, if we do alpha star beta or beta star alpha, we get 0. And that's our definition. So we're simply saying that this is how these spin functions operate. Now, what this means is if I apply this to the broader scheme of things, and if I have a total wave function, now I'm including my m sub s here. So if my m sub s is +1/2, I simply apply this alpha term into my wave function. And now if I want to make sure my wave function is orthonormal, so say if I wanted to do the quadruple integral now of my wave function, so this is a 1s orbital, but here we have an electron with a spin up, and here we have an electron with a spin down. I need to do this quadruple integral, which simply boils down to the triple integral that I had before. And remember, this integral, since this is the square of the magnitude of these wave functions over its respective area of integration, that gives me 1, because this is a normalized wave function. But now I have alpha star beta d sigma, and since those are orthogonal to each other, that gives me 0. And so my new wave functions, right, my psi star 1, my psi 1 0 0 1/2, and my psi 1 0 0 -1/2 are still orthogonal to each other. They still are part of this orthonormal set. Essentially, what we're doing here is providing some mathematical formalism to be able to incorporate this relatively abstract concept of electron spin into our Schrödinger equation. The last thing we need to be able to discuss before we can get a full picture of the wave function for these multi-electron atoms is the indistinguishability of electrons. So what do I mean when I say the indistinguishability of electrons? Well, we can't tell two electrons apart, right? So we had this nomenclature, right? We had an electron 1, we had an electron 2, because there are 2 electrons. But there's not an electron that's labeled 1 and an electron labeled 2. I don't know which one is 1 and which one is 2. And if I were to switch them, right? I wouldn't be able to tell anything has changed. Just like if I rotate a diatomic model 180 degrees, I can't tell that anything has changed there. So how can we incorporate this? We need to get what we can measure and make sure that that is the same, right? We measure the same thing whether or not our electron, if we switch the positions of electron 1 and 2. And remember, what we're measuring is not the wave function, it is the square of the magnitude of the wave function. And so what can we do here? Well, we need to ensure then that the square of our magnitude of our wave function, and here I'm writing 1, 2, and when I write 1, 2 in this way, my 1 is now all of the variables for electron 1, and 2 is all of the variables for electron 2. So if I were to completely swap those, if I were to say now my wave function, instead of being a function of 1, 2, is a function of 2, 1, and of course I'm always squaring that, these two need to be equal to each other. And when we do this, there are two very straightforward options that come out of this thing. We could have what's called a symmetric solution where psi 1, 2 is equal to psi 2, 1. And we could have an anti-symmetric solution where psi 1, 2 is equal to negative psi 2, 1. And since we're squaring these, of course, both of those are going to be equal to each other. So x squared is equal to negative x squared. They'll both end up being x squared. And this gets us into our final quantum mechanical postulate. So you'll recall in chapter 14, we left off the sixth and final quantum mechanical postulate because it dealt with multi-electron systems. And now we are finally attempting to talk about multi-electron systems. So we need to resort to that and bring it back in. And that quantum mechanical postulate is also known as the Pauli Exclusion Principle. It has a much more obtuse form than it does when we say two electrons have to have different sets of quantum numbers. So our sixth quantum mechanical postulate that we will be able to convert into the Pauli exclusion principle is that wave functions describing a many electron system must change sign under the exchange of any two electrons. And what does that mean? Well, if we go back one slide here, that means that we have to have this anti-symmetric wave function. So symmetric wave functions will not provide good solutions to our Schrödinger equation. We have to have anti-symmetric wave functions. They have to change sign. Now, how can we do this, right? So I just mentioned we have to have these anti-symmetric wave functions, but how can we make sure our wave functions are anti-symmetric? And it turns out that the way to make sure our wave functions are anti-symmetric are by constructing Slater determinants. And if you haven't taken linear algebra, you probably haven't had too much experience with determinants, but rest assured they are relatively easy to determine. So determinants are a way to talk about matrices. And if we have, for example, a 2x2 matrix where we have A, B, C, D in our 4 entries here of our 2x2 matrix, to construct the determinant, what we simply do is take A times D and then we subtract C times B. And that's what's shown here. And this gives us a single number that is the determinant of the matrix. And we'll go through some examples of this on the homework and then in class as well. And then in class, we'll talk about 3x3 determinants. So for a large matrix, or for constructing a wave function, we can use a determinant of this fashion, where outside we have a normalization constant, which is 1 over n, the number of electrons factorial. And then inside we get the following. In the first column, we have our first eigenfunction here, which corresponds to our 1s orbital. And then we give this first column 1s orbital spin up. And then in the rows of this first column are all of the electrons. So we have electron 1 in the 1s orbital spin up, electron 2 in the 1s orbital spin up, and then 3, 4, 5, all the way down to electron n in the 1s orbital with spin up. And then in the columns, we start placing the next orbitals. So this next section will be the 1s orbital spin down, and then the 1s for electron 1, and then the electron 2 in the 1s orbital spin down, and so forth. And then the third column going down the rows will still be electron 1, 2, 3, 4. But in the third column would be, say, the 2s orbital spin up, and then the fourth column would be the 2s orbital spin down, and so forth until we hit the end here. And this is going to be how we can construct these Slater determinants to construct these antisymmetric wave functions. So let's look at the helium atom, and we'll probably do lithium in class to get an idea of what we can do here and more in depth of why we use these. So for helium, we would construct this wave function as the following. So our n is 2, so 1 over 2 square root of 2 factorial is 1 over the square root of 2. And then we would have, again, 1s1 alpha 1, so 1s orbital spin up for electron 1, 1s orbital spin up for electron 2, 1s orbital spin down for electron 1, 1s orbital spin down for electron 2. And then when we were to construct the determinant, we multiply this term by this term and then subtract the product of this term times this term. And so for the homework for today, you're going to be looking at this wave function and swapping electrons 1 and 2 and seeing that that does in fact give us a negative value of our starting wave function, which means that this is an antisymmetric wave function. And if we were to take the square of this, we would get the same thing for 2, 1 as for 1, 2. So our determinants are a useful way of building up these antisymmetric wave functions, but why do they have to be antisymmetric? What's going on with our Pauli exclusion principle here? What this does is it shows that for determinants, they have a couple of nice properties. So one, if we were to swap B and D with A and C, swap those two columns, our determinant automatically becomes negative, which is exactly what we want. So it constructs our wave functions here. But what it also does is that any two rows or columns of our determinant are identical, the value of the determinant is equal to 0. So what this says is that if we try to put two electrons in the same orbital with the same set of quantum numbers, we'll have columns or rows that are identical. And what that will give us is a wave function of 0 or a wave function that doesn't exist. So this ensures, constructing our wave functions in this way, that our electrons have a unique set of quantum numbers, which is what we expect from Pauli's exclusion principle. So to conclude here, we use our Slater determinants in this way because it makes sure our wave function is 0 if we try to violate this kind of Gen Chem definition of Pauli's exclusion principle that we had, that our electrons must be in having a unique set of quantum numbers. So I'll finish with this here. And next time we're going to look into maybe some more real ways of solving this Schrödinger equation. So we'll look at some computational ways that we can more accurately determine the solutions to these equations that we can't analytically solve.